And yeah, so anyway, it is great to see all of you guys. And we've got a few things just for announcements, and then we're going to jump right in. Don't forget, there is a homework assignment due today. I have had a few people coming to my office hours so far, both in Zoom and in person. So that's been great. And I do have office hours later today as well. I'll also try to take a few questions off of the assignment during our class today. A few people have put some things on the board over here that we can look at as well to practice, but hopefully you will be able to get that homework done by tonight. There is another assignment. There's always another one waiting in the wings. The next one will be due on Friday. I normally don't have office hours on Fridays, but I probably will add some this Friday. The reason is that, well, we'll probably be covering some of that material even on Thursday. And so just getting the homework done for Friday, I want to give you an extra day to get it done rather than having to turn in the homework the same day that we're talking about it. So that's the schedule for this week. Homework number 10 is due tonight. Number 11 is due Friday night. We're almost halfway through the semester. I know that because this is week 7 out of 15. I also know it because there's a total of 24 homeworks for this class for the whole semester, and we're almost up to number 12, which will put us halfway there. So we're kind of almost halfway with everything. And we are right smack dab in the middle of chapter 4, which I know is kind of a long one. Takes a while to kind of get these vector space ideas down, and it's a little bit abstract, but we are getting there. We are getting there. We should finish chapter 4 this week and be talking about chapter 5 by next week. So that's the game plan. Let me just recap for you where we kind of left off 5 days ago. We were talking about a vector space V, of course. That's what the whole chapter is about. In a vector space, you know, we have it's some universe of vectors, right? And we've got a pretty good little list of vector spaces that we've mostly been exploring, right? We have polynomials is a vector space. Matrices can form a vector space. Calculus functions can form a vector space. Traditional physics vectors in 2 or 3 or 4 or n dimensions can form a vector space. So we have these examples of vector spaces. And last week, guys, what we were doing last week is we are grabbing a handful of vectors from our vector space, and we're going to ask 2 questions about them. Actually, ultimately, it's going to be one big question about them, and this is the way I'm going to ask the question on the midterm, is the way it's listed on the bottom of the board here. But before I get to that, the 2 questions that we are interested in are as follows. First of all, does that set of vectors V1 through Vk, it's just some handful of vectors in this universe, do they form a spanning set for V? In other words, do they span V, right? So that's the first question. And we have discussed this already quite a bit, and we've done a number of examples. The idea is you're asking yourself, if you form linear combinations, all possible linear combinations of V1, V2, V3, and so on, if you make those linear combinations, which looks like this, right? C1 times V1 plus C2 times V2 plus C3 times V3. If you write that down, can you make it equal to any vector in V whatsoever? And I'm writing that here as kind of a number symbol, hashtag symbol vector, right? Because that's representing an arbitrary vector in the vector space. Okay? So here's the question. Given that linear combination in blue, can we solve it for C1, C2, C3, and so on? Well, so it's a system of equations, right? We did this last week. We said, let's put it into a matrix. What we noticed last week when we did that is that the original vectors end up in the columns of this matrix, and we augment the matrix with that hashtag number symbol vector. So you see in the far right column, and again, it's not really drawn this way in the book, but in the far right column, you just have number symbols, okay? And all you're going to do with that matrix is bring it into row echelon form, circle your pivots, and determine whether the system is consistent or not. We actually don't have to solve the system. We just want to know, can we solve the system? If it's yes, right, then yes, we have a spanning set. If it's no, then no, we don't have a spanning set. Okay? Now this all comes down to whether the pivots end up in the far, far, far right column or not. Okay? That's one question. And this, by the way, this part is coming in the book, of course. This was section 4.4. We talked about that last week. Right? So I'm just reminding you here. This should be review at this point, right? I give you a set of vectors. Are they a spanning set for V? Great. Throw them into a matrix, row reduce it, and just figure out whether the pivots are in the far right column or not. In other words, whether it's consistent or not, and that gives you your answer. Easy peasy. That's what you're doing for tonight's homework, actually. Part of tonight's homework is just to do that. Then there's a second question that we want to follow up with now, which is that we don't just want our vectors to span V. We're not only interested in having a spanning set, we want to make it a cheap spanning set. We would like to span V using what's called a linearly independent set of vectors. Right? So we don't want, imagine that it costs you $1,000 for every vector that's in your spanning set, right? You would like to get away as cheap as possible using as few vectors as possible. And the way we formalize that is with this idea of linear independence. Now, I did ask you to watch a short video over the weekend with me going through a few examples of this. The basic idea of linear independence, actually, believe it or not, guys, it's the same exact linear combination again. C1, V1 plus C2, V2 plus C3, V3, and so on. But there's one difference, which is that on the right-hand side of the equal sign, instead of trying to express an arbitrary vector using this linear combination, now what we're hoping to do is we're hoping to set it equal to 0. Okay? And so it's almost the same thing. The stuff in blue here is almost the same as the stuff in blue here, right? Let me just remind you where this is all coming from before I go into the rest of this recap. On the board over here, I have reminded you, hopefully this looks a little bit familiar. I have reminded you about what linear dependence means as a definition. Remember, linear dependence, this is, bad. We don't really want LD. We really want our vectors to be LI. If the vectors are LD, that actually means that we did spend too much money on those vectors, right? We don't want to do that. What does LD mean? Well, my vectors are LD if I can build a linear combination of them that cancels out completely, but I did it without cheating. I did it without just putting zeros in front of all the vectors. In other words, if there is an interesting way to get your vectors to cancel out, then your vectors are LD. If there's a way of making them cancel out without all of the scalars being 0, then the vectors are LD. We wrote this down last time, right, on Thursday. This is the definition of linear dependence. Now, what I didn't write down on Thursday, which I do want to write down now, is I would like to take that rephrased point of view about linear dependence and rephrase the opposite idea right along with it. So this is probably not in your notes yet, the rephrased version of what LI means. Like, what does LI really mean? Well, I'm going to do it for you right here. The set V1, comma, V2, comma, dot, 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 up to VK is LI if and only if, okay, it should be the opposite of what LD is. LD says I can make my vectors cancel out in an interesting way without making all of the constants equal to 0. The opposite of that would be that the only way that you can cancel your vectors out in a linear combination is by cheating and putting zeros in front of all the vectors, right? So let's write that down. The only way to have C1 times V1 plus C2 times V2 and plus so on and so on up to CK times VK equal to 0. The only way to have your vectors canceling out in a linear combination is if C1 equals C2 equals dot 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 equals CK equals 0. Every single scalar is 0. If that's the only way that you can cancel your vectors out in a linear combination, then those vectors are good vectors. They are Li. You see what I mean? This is the good scenario. This is what we want. This is what we want. But you'll notice, guys, that in this definition, we see that same linear combination. That same linear combination that we were looking at when we were looking at spanning sets is showing up again in the definition of Li, except instead of number symbol, now I'm putting 0 there. Now I'm putting zeros. See what I mean? Is everybody with me? Any questions yet? Hopefully it's clear so far. Well, so of course, with this blue equation here, I'm going to do the same exact thing. I'm going to put it into a matrix again, exactly in the same way. So instead of augmenting with a number symbol, now I'm augmenting with 0. Now, as soon as I augment with 0, let me ask you, could you ever have a pivot in the far right column of if the whole column is just zeros? Oh, definitely not. A column of zeros is never going to have a pivot in it, which means this system is always consistent, right? We don't have this yes/no question about whether it's consistent or not. In this case, it's a 100% certainty that this system will be consistent. What's the bigger issue here is whether we can solve the system with just all of the constants being equal to 0. That would be Li, or whether it's possible to solve for those unknowns with other constants that are not all 0. That's really the question. In other words, is there only one solution to this system? Or are there many solutions to this system? Remember, you guys know, right? Every linear system has either no solutions, one solution, or infinitely many. In the case when the far right augmented column is all zeros, then you won't have no solutions. You will definitely have a solution. The only question is there one solution, which would be the trivial one with all of the constants being 0, or are there infinitely many solutions? And the difference between those two outcomes is really the difference of whether there are any, you want to tell me? Say it again. Free variables, exactly. If there are free variables, right, that's how you get infinitely many solutions. So if there are free variables, my friends, that's actually bad here. That actually means there's lots of solutions for the C1, C2, C3, and so on. And that would mean, no, these vectors are not Li. But if there are no free variables, that's actually a good thing here. That means, hey, there's only going to be one solution to the system, and that one solution will be with all of the constants equal to 0. You see? So that's kind of how this works. And this is really the whole topic of section 4.5. So the two sections are kind of back to back here. And what we're going to be doing today is kind of 4.6, where we're going to put all of this together. And the way that it's going to get put together is I'm going to give you a set of vectors now. And instead of just asking you if they're a spanning set, and instead of just asking you if they are Li, I'm going to ask you both questions. I'm going to ask you both questions at once. And I'm going to say, is it a spanning set? Is it Li? Is it both, or is it neither? So it's all of a sudden going to be a 4-part multiple choice question, is what it is. And this is the way I usually ask it on the exams. The homework won't always do that. Of course, in 4.4, it's just going to be talking only about the spanning question. 4.5 is only about the Li question. But now we're going to start putting them together and asking both questions at once. Why do I want to think of them both at once? Well, it's because the matrix that you're going to end up writing down is almost the same. And I would hate to like do all this work and then start over and do all this work. It seems like it should be possible to just do them at once, and it actually is. So for this problem, all right, let me just make a note here. I guess I'll use my black marker for this one as well. So quick remark here, guys. The remark is that we can answer both of these questions at once. So let me see how I want to do this. We can answer 1 and 2 above simultaneously. And you know how we do that? What we're going to do is we're going to set up the matrix. First column is V1, second column is V2. We're going to go dot, dot, dot. And the kth column is VK. And then I'm going to have my augmenting that I do. I augment the matrix here. And what I'm going to do in the far right column, guys, is I'm actually going to write 0 vector / number symbol. So I'm going to put both of those notations kind of with a slash on the far right column, because what I could do, guys, when I do EROs, the zeros just stay zeros. And when I do EROs, the hashtags just stay as hashtags. So you don't really have to use your brain very much over here. You're just going to be recopying all the zeros and all the hashtags every time. What really matters is doing the EROs here on the left side and just checking out where the pivots end up. That's actually what's really going to matter. Okay. So, and what my point is I only want to do those EROs once. So I'm going to do them only once. I'm going to multitask here, and I'm going to answer both questions over there with just one calculation. You see what I mean? Let's actually try an example of that, unless there's a question so far. Everybody good with this so far? Okay, so let's do, I've got an example. So if you watched my 15-minute video, you saw me do a couple of quick examples in that video. I hope that you all watched that, because I'm not going to do those examples again. Instead, I'm going to give you a different example. Let's do this example. Let's let V, I'm going to start, I always like to start with an example that's pretty familiar. Let's take R3. And I'm going to make a set of vectors here. I'm going to call it S, and S is going to have the vector 1, 1, 1, 2, 0, 6, and 4, 2, 2. And by the way, I know that this is a little bit of a hiccup with the notation. I know that we've frequently been using S to represent a subspace. And so when people see S, then, oh, that must be a subspace. Of course, these 3 vectors by themselves are not going to be a subspace. I don't even have the 0 vector in the list here. So it's not even going to pass that test. This is literally just a set of vectors. Okay. So I'm just calling that my set of vectors. We can, of course, identify, the first vector is V1, the second vector is V2, and the third vector is V. So in the notation, that's the way I would think about it. And now here's the question. Is S a spanning set? Is it Li? Is it both? Or is it neither? So I'd like to practice this multiple choice problem. Like I said, I always have these on my exams, phrased pretty much exactly like that. And so let's see how this would work. So for the solution, as you guys hopefully are comfortable by now, we're going to take each vector and lay them vertically into the columns of a matrix. So the first column would be 1, 1, 1. And then the second column would be 2, 0, 6. The third column would be 4, 2, and 2. And I'll just remind you, the unknowns in this linear system are constants. I'm going to label them as C1, C2, and C3. Okay, I would recommend you think of it that way. Somebody was in my office hours earlier today using XYZ for that. It's not really wrong, but XYZ doesn't remind me about this material very well. So I like to use C1, C2, C3. And then I'm going to augment this matrix with 0 hashtag, 0/hashtag, 0/hashtag. I am going to solve both of these questions, right, in one breath. I'm going to do them both at the same time. Okay. So of course, what I'm going to do is I'm going to do EROs, but remember, I don't have to really turn on my brain on the far right column. The zeros just stay zeros, the hashtags just stay hashtags, and all I'm really doing is just recopying that far right column every single time. It's what's happening on the left side that really matters. So I probably should start off by leaving the first row the same. I'm going to circle a pivot around that first one that we see there. And then I'm going to try to get zeros below that leading pivot. So to do that, I just look at my numbers here and I see, okay, I'm going to do A12 of -1 and also A13 of -1. Those are the EROs that I'm going to use. So I'm taking the negative of the first row and adding it to the second row. So I should get 0, -2, -2. But see, the far right column is still just zeros and hashtags. I don't have to think about what it really becomes. And in the bottom row, I do something similar. The negative of the first row added to the bottom row gives me 0, 4, and -2. And again, we have a 0 and a hashtag. Okay, perfect. So essentially, this is going to be a pivot right here. You're going to notice me getting a little sloppier about like actually making the pivots into ones. I don't really need to do that. But if I'm trying to decide whether my systems have, you know, no solutions, one solution, or infinitely many solutions, what's really important is the positions of the pivots, not necessarily that the pivots are ones. Okay, so I'm perfectly happy circling that. It's the first non-zero entry in the second row. And I'm going to do one more ERO now, which is A23 of 2. So I'm going to leave the first row the same. First row stays the same. Second row stays the same. It's not changing that at all. But what I'm going to do is I'm going to double the second row and add it to the third row in order to get a 0 below this pivot. So 2 times the second row added to the third row, I believe that gives you 0, 0, and -6, and just 0 and hashtag here. And so I should circle the -6. And this is, of course, not officially row echelon form because the pivots are not ones yet, but it's good enough for our purposes of answering this question. Would somebody like to answer the question based on those pivots? Is S going to be a spanning set, linearly independent, both, or neither? Both. Got both? Both? Yeah, it's going to be both, right? Come back over here. If you're not sure, come back over. This is a, if you haven't got this notes down yet, I would take a picture of this board. It's like really, really good summary of how to deal with chapter 4. So I look at my matrix and is it consistent? Yes or no? So I look over here, I say, yep, it's definitely consistent. There's no pivot in the far right column. That's good. Okay. And then is there any free variables? Yes or no? And again, I look at this, I say, nope, there's no free variables here. That means that C1, C2, and C3 would have to be 0. The only way to get these vectors to cancel out would be by putting zeros in front of each vector, which is kind of the cheap way of doing it. And so there's no free variables. So we get a yes and a yes, and that means it is both. It is both. So let me just make the comment here. There's no free variables. We can see that directly from this pivot structure, and it is consistent. And so that's great news. That means it spans R3 and it's Li. It's a spanning set and it's as cheap as possible. We did not waste $1,000 here, right? We needed every one of these vectors. Were you raising your hand, Destina?
With this room.
This remark here? Kind of, yeah. I'll write down a definition in a minute. We'll officially start 4.6. Yes.
Oh, how is it consistent?
It's consistent because there's no pivot in the far right column. That's all you have to know.
And no free variable.
And there's no free variables either, which means it's Li.
So it's both
Exactly.
a spanning set and.
It's both. Did I circle it? Yeah, I definitely circled it. Was there another hand? Riley,
Would there be any like formal answer, or can we just say both?
you would just say both. Of course, I'm gonna want to see your work. So if it's on a test, which something like this will surely be on a test. You would set up the matrix, you would do your EROs, you would circle your pivots, and then you can, once you have this, you can pretty much go straight to the answer. Yeah, Tony, and then Adrian, yeah.
What does it look like with the free variables?
If there was a free variables, let's do another example. We'll see. I'm gonna show you lots of examples of this that you're gonna see. Basically, if there's free variables, then what would happen is on the bottom row, you would have 0, 0, and 0. And if you had that, then this third column doesn't have a pivot. That means that C3 would have been free in that case. Right, Adrian?
I heard you go over, but can you go over again how come the -2 doesn't turn, like, well, how come we don't care about the ones and?
We could change them to ones if we wanted by multiplying these rows through by the reciprocals of whatever the number is there. But it's not really important in terms of answering these issues. Will the system be consistent or not? And are there free variables or not? I don't really need those pivots to be ones, and I'd just like to save a little time. Because, yeah, to answer these questions, what's more important is just the positions of the pivots and not anything else. Everybody with me? Good questions. This is good stuff. There is a special name for a set of vectors that is both a spanning set and linearly independent. And the name is probably the most important word in the entire theory of vector spaces, is a basis for the vector space, a basis. And that is what this next section is about. So try to make Destina happy here. I'm going to put the 4.6 up here. This is the section called basis and dimension. Basis and dimension. This is the whole point of what we're talking about. So let's write down a definition. Right? So the definition is that a set S of vectors in V is a basis for V if two things are true. First of all, S spans V. So it needs to be a spanning set for V. And secondly, S is Li. So that's a good place to start this new section. The definition of a basis. A basis should be a spanning set. It is also Li. So in R3, we have now given an example of a basis, right? So we have a both. Anytime the answer is both, then that's a basis. So I've got a good 111, 206, 422. That is a basis for R3. So just let's write that down actually. Example 111, 206, and 422 is a basis for R3. That is a basis for R3, right? Do you think it would be the only basis for R3? I mean, we think about it, if we took our vectors and laid them out in the columns, would it have to be exactly these numbers in order to have the pivots end up like that? I don't think so. I don't think so. I think you could find lots of other examples. Let's just write down another one. Another example, I'm going to write down something that'll be really easy. How about 1, 0, 0, and then I'll use 2, 3, 0, and then 4, 5, 6. I claim that that is a basis for R3. Would you like to see why in like 2 seconds or less? It's so easy. You just put these vectors into the columns of a matrix, right? And notice that I chose such a nice set because they're already in row echelon form. So you set up your matrix just like before, but this time I don't even have to do any EROs. I've already got my pivots kind of working the same way that they did here, just with a lot less effort because of the nature of the set that I wrote down. See, there's no free variables. and there's no pivot into the far right column. So this is another basis. What do you think would be like the easiest basis on the whole planet that we could give for R3? Can somebody give me another basis here that might be like even more obvious? Like what would be like the most obvious basis you could ever imagine for R3? You can already see it in your head that when you put it into the matrix, you're gonna have pivots that go right down the main diagonal. What would be the most obvious one of all? Adrian?
Would be 1, 0, I mean, one's like diagonally.
Uh-huh. Yeah, absolutely. So is that what you were gonna say?
Yeah, 1 0 0 0.
Beautiful. 1 0 0 and then 0 1 0 and then 0 0 1. I can't think of a better example. In fact, this one is so nice that this has a special reference. We call it the standard basis for R3. So this one is a basis for R3. This is even more than that. This is the standard basis for R3. Right, it's like the nicest basis that you could have for R3. If you draw the matrix for this, it is exactly the identity matrix, which doesn't get much nicer than that. The pivots go right down the main diagonal. See what I mean? So I guess we have to make a remark here then. The remark that we have to make is that a basis for a vector space, it's a nice idea, but it's not unique. There is not just one right answer, right? So a basis for a vector space does not have to be unique. Everybody understands the word unique, I hope? Unique would mean if there's only one. If there's only one basis, we would say it's unique. But you see, there's lots of bases. Lots of bases. We could go on all day. We could go on all day making many, many more, right? Any 3 vectors that would fill up a matrix like this and the EROs lead to pivots down the main diagonal is another example. Okay. So basis is not unique. You're checking your answer in the back of the book. Well, their answer might not be the same as yours. Because if they say find a basis, there could be many right answers. Just keep that in mind. But there is something about all of these bases that is shared in common between them. And I don't know if anybody has an idea what it is right now. Oh my gosh, this morning I had first class. I must have called on 10 people and couldn't quite get the answer out of them. So I don't know. Does anybody think they might know, Destina? Somebody this morning said that. It's not wrong. It's just, you're right. When I do the EROs, the matrix goes into this upper triangular form. That is certainly going to happen with any basis. But I'm talking about something that's just really obvious. Bring your 8-year-old cousin into the room or something, and they look at these 3 examples and they can tell me something that's the same about all 3 of them. They've never heard of a vector space before. They have no idea who Dr. Annan is. They just walk in the room and they look at this set, they look at this set, they look at this set, and there's something about them that's the same. Yes. Not what I was looking for, but good try. You're right, they would form an n by n matrix. Something really obvious, an 8-year-old doesn't know what a matrix is. Yes. That is true. That's a lucky coincidence here. And an 8-year-old would know that, but that is not actually what I'm looking for. You want to give it a try? Well, this is the pivots are going down the main diagonal. Yes, that is true. But again, too specific. I'm looking for something really easy. You want to crash and burn too? Give it a try.
The first vector has 0 0 at the end, the second vector has a 0 at the end.
No. That's not what I'm looking for. Okay, guys, let me ask you this question. I'm just gonna, apparently this is stumping everybody. How many vectors do I have here? 3. How many vectors do I have here? 3. How many vectors do I have here? 3. The number of vectors. That is actually what I was looking for. I don't see any basis here that has 4 vectors in it. I don't see any basis here that has 2 vectors in it. For R3, every basis that we would write down has exactly 4 vectors in it. You see that now? That makes sense? That is called the dimension of the vector space. This number, this correct number of vectors in the basis. So all of these examples have 3 vectors in them. So let's come over here. I'm going to erase this very good summary with these 2 questions on it, and I'm going to write down the idea of the dimension of the vector space. And then we're going to do some more examples in other vector spaces besides just R3. So definition here. Well, actually, before we do the definition, just a remark first. I'm sorry, just a quick remark. The remark would be every basis for a vector space, every basis for a vector space contains the same number of vectors. That's actually a relatively deep result on linear algebra. Like, we actually wanted to prove this from the definition about, it has to be a spanning set, it has to be Li, right? To actually prove this remark would really take a little more sophistication than we have right now. It's the kind of thing I talk about when I teach Math 307, which is our sort of more theoretical upper division math major linear algebra course. We're going to kind of just take it as an observation, from the examples that we're seeing, that every basis for a vector space must have the same number of vectors. Okay, and so then we can give the definition, which is the dimension of V. The dimension of V, and this is usually just written as dim of V. Dim of V. This is the number of vectors in any basis for V. So you can take any basis whatsoever. The dimension of that vector space is just how many vectors are in that basis. So obviously our first example of this would be that the dimension of R3 is equal to what? 3. Thank you. 3. Exactly. And we have plenty of examples here. We have 3 different bases for R3. They all have 3 vectors in them. I'm wondering if anybody would like to take a guess at what would be the dimension of any Rn. So if instead of R3, if it was R4 or R5 or R6, because those are all vector spaces that we are interested in. If we tried to press on to any Rn, what would be the guess for what this number should be if everything is right with the world? Liam? Just n. It's just going to be n, right? And the way I can hopefully convince you that that's the right answer very quickly is to just give you the standard basis for Rn, right? So what would be, let's put this right below the formula here, a standard basis for Rn, we can actually explain what that is pretty easily. What I'm going to do is make a set where the first slot is 1, 0, 0, 0, 0, 0, 0, 0, right? I mean, I'm kind of following the model of this. This was the standard basis for R3. Notice what happened here is that the 1 just kept moving to a different slot. Here, the 1 is in the first slot. Here, it's in the second slot. Here, it's in the third slot. I can do that same thing here as well. So the second vector would be 0, 1, 0, 0, 0, 0, 0, 0, dot, dot, dot. And so on, the very last vector here would be 0, 0, 0, 0, and then a 1 at the end. And if you think about, well, how many vectors are listed there? 1, there's 2, there's n slots. So this is a basis of Rn. It has exactly n vectors in it. And so the dimension of Rn would be n. If you took these vectors and laid them into the columns of a matrix, it would look just like an identity matrix. So like this one would have been, 1 0 0 0 1 0 0 0 1, right? So you'd have exactly your identity matrix there, and there's no reason why we have to stop at a 3 by 3. This would work for n equals 4, n equals 5, n equals any number. Right? Okay, so that's a good observation. I would like to point out that if we know numbers like this in advance, which by the way, you need to burn this into your memory, for sure, memorize that number. If we know the dimension of a vector space in advance, it can be really helpful when we go back to our 4-part question. Because then what happens when I come along with a set of vectors that has the wrong number of vectors in it? So let's say I gave you 4 vectors in R3. Well, then you know the answer is not both. You have the 4 choices, spanning set, Li, both, or neither. It wouldn't be both if it was 4 vectors, because that's too many vectors to be a basis for R3. Or if I only gave you 2 vectors in R3, that's not enough vectors. That couldn't be a both either. So this dimension concept, even though we're now covering it after we've talked about the spanning sets and Li, this dimension concept is actually going to be useful and help inform us about sets of vectors, whether they would be spanning sets, Li, both, or neither. So we're going to come back to that point in just a little while today. But this is all connected together, you see. Before I do that, though, I want to give you an example of something other than just R3, because R3 is, almost too comfortable for us, I think, sometimes. So I'm going to come over here and write down another example, if that's okay. So let's do an example here. Ready? So let's do this one. Let's take P3 of R. And I'm going to take my set S this time to be the following vectors, okay? I'm going to use 1, X, I'm going to use 1, and then I'm going to use 1 plus X, and then I'm going to use 1 plus X squared, and then I'm going to use 1 plus X squared plus X cubed, and then I'm going to use X plus X cubed. So I'm going to make those 5 vectors there. Like before, we can label them. So the first one is V1, the second one is V2, the third one I'll call it V3, the fourth one is V4, and the fifth one is V5. We've got 5 vectors this time. And I'm going to just go back to the original question. I'm going to ask, is S a spanning set? Li, both, or neither? We're going to ask the same question that we played with R3, but now we're going to do it with polynomials. Okay? So that's the problem. Now, we actually did this one on Thursday last week. If it looks familiar to you, we've actually already looked at this exact example. But I'm going to do it now with my sort of new and improved process where I just lay the vectors into the columns of the matrix and augment it with zeros and hashtags. We're just going to do it that way. Okay, so how's that going to look? Well, I'm going to take the first vector. I'm going to go straight to the matrix, guys. I'm going to take the first vector, which is 1, and I'm going to lay it into the first column. Does anybody remember how that should look when I lay the 1 all the way into the first column here? David?
1 0 0 0.
Just that much, yeah, exactly. So remember that 1 is really the way you can think about that is it's 1 times 1 plus 0x plus 0x squared plus 0x cubed. And if you grab these scalars, the 1, the 0, the 0, the 0, you build that first column, you see, those coefficients there. So that's how you do it. How would the second column look? One, no plus signs. I just want, what numbers go in the second column?
1, 1, 0, 0.
1, 1, 0, and 0. Beautiful. Just those scalars right there. What about the third column?
1, 1, 0.
1, 1, 1, 0. Beautiful. And how about the fourth column? All ones, right? 1, 1, 1, 1. And then the fifth column has no x, no constant term. It has 1x. It has no x squared. It has 1x cubed. Okay, so that's my matrix. I'm going to augment that with 0/number symbols. Okay, so I'm going back to this 4-part question. And one of the reasons I wanted to use this example is I don't have to do a single ERO on it. I can just simply go straight to circling my pivots. It's already in row echelon form. I will circle my pivots like that. And then I'm going to ask you now, with those pivots, and remember the unknowns are lined up with these columns, and I like to think of them as C1, C2, C3, C4, and C5. Based on that matrix, does anybody think they know the correct answer to the multiple choice question? Are these vectors a spanning set? Are they Li, or are they both, or are they neither? What would you say in this case? Angela?
It will be LD in the spanning set.
It will be a spanning set only, right? It's not Li. It's a spanning set, but it's not Li. Why not? It's not Li because, guys, look right here. C5 is free. There is no pivot. Somebody asked me, I think, earlier, what would it look like if there was a free variable? Here you have it. There's a column that has no pivot in it. That means that's a free variable, and free variables are bad. Free variables mean that C5 is not necessarily 0. It's equal to T, in fact, and T could be anything, right? So, so this is not Li, but it is a spanning set because, after all, the pivots did not go all the way over here to the far right column. So it is a spanning set. I would agree with that. So if we wanted to, guys, maybe I'll take just a minute and do this. I did this quite a bit in the video, that the 15-minute little video that I hope that you watched over the weekend, but I can now solve for C4, C3, C2, and C1 by back substitution, right? So using this, if C5 is equal to T, see, take a look at this bottom row. The bottom row tells me C4 plus C5 adds up to 0. So what's C4 going to be equal to? Imtina?
So C4 would be negative T.
Negative T. Exactly. Because when you add C4 plus C5, you should get 0. So if C5 is T, then C4 should be negative T. Okay, and then I can go to the previous equation, which is, C3 plus C4 has to add up to 0. So C3 and C4 also have to cancel out. So C3 is back to positive T again. And then, well, from the previous equation, it looks like C2 plus C3 plus C4 plus C5, they all have to add up to 0. And so far, if I add up what I have so far here, I have T, negative T, and T. So to get it to all cancel out, I need another negative T. So C2 is negative T. And then finally, the first 4 constants from the first row, C1, C2, C3, and C4, they have to add up to 0 as well. So I look at these constants and it has to be T. I'm just doing it quickly. Okay, so those are the values of T. And then do you remember what I did in my video when I had one of these in the video, I think, over the weekend? What do I want to do now with the T value? I need to choose a number for T, right? I'm trying to make a linear dependency here. It's not me. They didn't ask us that. Like, we're already done with the problem, guys. We're already done with this problem. We already know it's a spanning set. I'm just kind of indulging for a minute, saying, well, what else could we do with this? We can actually put in a number for t, and I like to choose t to be equal to 1. But any number is okay, except there's one number you should not use here. 0. Exactly. If you put in t equals 0, you're going to get all the constants to be 0, which is not showing me that the vectors are LD. So I need to choose, let's just do it. I will choose t equal to 1. Okay, so then I'm going to come over here and I'm just going to write down if t is equal to 1, then I have 1 times v1 minus 1 times v2 plus 1 times v3 minus 1 times v4 plus 1 times v5 adds up to 0. And that is your linear dependency. Right. That is your linear dependency. So, you know, what we're saying is first vector minus the second vector plus the third vector minus the fourth vector plus the fifth vector will cancel out to 0. So these vectors are LD. We spent $5,000 on these vectors. They did span P3 of R. They did span P3 of R, but we spent $5,000 doing it. And that was too much money because if the vectors are LD, that's essentially what that's telling us. So I'm wondering if there's a way to fix it. Could we somehow salvage this set S? It's sort of good. At least it did what we wanted. It was a spanning set. That after all, that's a good thing. But I want to get a cheaper spanning set. I would like to not have the vectors being LD. Is there something we could do to salvage this example and end up with actually a full-blown basis? They're already halfway to being a basis. They are a spanning set, but I don't have them Li yet. What could I do to now make this become Li? Marcus?
You take out vector 5.
Take out vector 5. Go back for a $1,000 refund. You're going to take vector 5 and you're going to say, if this column was not here, we would not have had a free variable anymore. And wouldn't that have been great? If that column wasn't, well, what would it take for this column to not be here? It would mean that this vector is not here, right? So you get rid of that vector and now look what you have. If you had this setup, you would have no free variables, but you still don't have a pivot in the far right column. That's a win-win, right? That means it's a spanning set and it's Li. In other words, it would be a basis. So just as a follow-up, I'll just add this over here in the notes now. As a follow-up, sorry, I have somebody actually attending in Zoom today, so I'm trying to do real good with my camera today. So as a follow-up, if we took just the first 4 vectors, 1 plus x, 1 plus x squared, 1 plus x squared plus x cubed, right? That is a basis for P3 of R, since we removed the vector v5, which was x plus x cubed, to remove the linear dependency. I'll just say the LD. We remove the LD by just throwing away that vector. Guys, this is something that will always work. This will always work. If you have a spanning set that is not yet a basis, this strategy will always work. Just take the spanning set, figure out which vectors are causing the problem. It might be multiple vectors. We could have had several columns that didn't have pivots, but whichever column or columns it is that don't have pivots, get rid of those corresponding vectors. Just throw them away. See what I mean? And then you're left with a set that still spans V, but now it's Li. Pretty neat idea. Now, somebody this morning asked me a very good question. They said, well, what if your set was Li to begin with, but did not yet span V? So you have a linearly independent set, but you don't have yet a spanning set. In that case, of course, you have to kind of think in reverse. Now it's like, I don't want to take vectors out. I want to add more vectors in, right? I want to beef up the span of my vectors, hopefully so that it would span the whole vector space. So I'll say a little bit more about that in just a few minutes. But yeah, we're trying to get both A and B to be true here. And by the way, a quick comment here. Can somebody tell me, I'll just call this more, another follow-up, I guess. Can somebody tell me what is the dimension of P3 of R based on what we've just done here? Maxwell? It's going to be 4. Remember, the dimension is just the number of vectors in any basis for V. And I have found a basis for P3 of R right here. 1, 2, 3, 4 vectors in that basis. So this is equal to 4. This is equal to 4. Okay. And again, that is not a unique basis. There can be many bases for a vector space. So we could write down others. Let me just see how your intuition is about this. I'm wondering if anybody has a kind of a thought about what might be the standard basis for P3 of R. I know that this word standard is kind of subjective, like there's no official mathematical definition for it. But what I'm talking about is, would there be sort of an absolutely nicest possible basis for P3 of R in the same way that the standard basis for Rn was just so easy? Lots of zeros and ones here. Can somebody think of a basis that would be 4 vectors in P3 of R? Maxwell, do you want to try it?
1 x squared x cubed.
I love it. I love it. Look how nice this is. This is 4 vectors. Beautiful. This is 4 vectors. And if I laid them out into a matrix, this would actually give you the identity matrix. If you put the columns of this matrix down, you'd have the identity matrix. The pivots go right down the main diagonal. That's exactly right. Since we're on a roll now, I'm going to go with another follow-up. Does anybody think they might know what would be the dimension of Pn of R if we were going to a general value of n? Do we have a guess as to what would be the right formula for that, Taylor?
N+1.
N+1. Wow, we are on a roll. I like that. N+1, and that's kind of natural once you think about what the standard basis would be. The standard basis here for Pn of R, what would it be? Well, you would just take powers of x, right? So you'd have 1x, x squared, and we would go dot, 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 all the way to x to the n. And that would work beautifully. And we can ask ourselves, well, how many vectors are in this list? And if you think about it, you're starting with x to the 0 and going all the way to x to the n. That's actually n+1 items there. Okay, so that is correct. I am going to put this in a box. Guys, I know that there's a lot of information on the board here, but the stuff that is going in those boxes for the dimensions, you need to memorize these. You really need to know these cold. So the dimension of Pn of R is n+1. Let's try another example. Yeah, I'll come back over here to the other board. Let's do one more example here, kind of finish this up, and then we'll take a little break. So again, if I give you 5 vectors in P3 of R, which is what I did right here, you know they can't be a basis. If I only give you 3 vectors in P3 of R, you know they can't be a basis. Right? If we know this magic number, it's as simple as counting. How many things did they give you? Honestly, the homework for Friday, some of the problems, you literally just gonna sit there and say, oh, there's 3 vectors here, but I know the dimension is supposed to be 4, so it's not a basis. And that's all you have to say. Like there will be some problems like that where you just literally have to count If you can count to 5 or something, you can answer the question, right? It's kind of that easy. But that does depend on knowing the dimensions ahead of time. Let's do one with matrices. So we'll do another example here. Just to practice, we've done R3, we've done a polynomial example. Let's do M2 of R for this one. So let's take 2 by 2 matrices. And I'm gonna make my set S, let's see, let's use 1, 2, 3, 4, right? Something like that. And then I'll go with 0, 1, 1, and 1. And then let's go with 0, 1, 3, 2. And then I'll go with, doesn't really matter. Let's take -1 and -4, oops, sorry, -1, -4, -7, and -7. Okay, so let's take that example. And I'm gonna ask the same question. Is S a spanning set? Li, both, or neither? So this time we're gonna play with matrices. Just kind of wondering if anybody has a guess. Nothing?
Not both.
It's not both, and you're basing that on,
Wait. Actually, no, it is both, I think.
it is both, okay, so he said no, then he said yes. David,
It's a spanning set and it's minimum
that's what you're thinking? Okay, hold that thought. What about you?
both.
Both. So you know, if you kind of have a sense what the dimension of this might be, then you can compare that with how many vectors there are. So those of you who are saying both are probably noticing that M2 of R is probably going to be 4-dimensional. And that is true, because after all, if I write down a 2 by 2 matrix and then I bust out the variables, how many matrices am I going to get when I do this? We've been practicing this idea, right? So we can create a spanning set out of these 4 matrices, right? That's my spanning set. Okay, so that's 4 vectors. And it actually turns out that those vectors are Li as well. So these vectors are Li, and therefore, actually this is, so let me just steal the thunder here. The standard basis for this, we can just add this to the notes right now. The standard basis for M2 of R is going to be exactly the 4 vectors that I have over there. 1, 0, 0, 0, comma, 0, 1, 0, 0, comma, 0, 0, 1, 0, comma, 0, 0, 0, 1. That is your standard basis for M2 of R. And so along with that, we then know the dimension. So the dimension of M2 of R is 4. And that is actually correct. And while I'm at it, by the way, these matrices where you have almost all zeros, but you have a 1 just in one spot, these are fairly well-known matrices to be pretty important. And so we can actually denote those with, you'll see this in the book, like this first matrix is denoted as E11, the second one is E12, the third one is E21, and the fourth one is E22. And so I'm getting away from solving my example here, guys, sorry. But we're kind of on the topic here, so I want to kind of flush this out a little bit further. Can somebody suggest to me what they think might be the correct formula for the dimension of Mn of R? Let's do this first, then we'll come back to this example. Tina.
N squared.
N squared, is that what you're gonna say? Absolutely right. It's gonna be n squared, and I can even tell you what the standard basis would be. The standard basis for this, very easy. Standard basis would be the set of all of these EIJs. So kind of these matrices up here, where in this case, both I and J have to go from 1 to n. So I have I and J values going from 1 to n. And just to be really clear, the EIJ matrix, this is a matrix that has a 1 in the ith row and the jth column. This is EIJ, and everywhere else in that matrix is a 0. So those are your, I mean, I probably should fill in. Yeah, 0, 0, 0, everywhere is 0, right? All around that one. You just have one spot where there happens to be a 1, and it's in the ith row and the jth column. And so there are n squared of those, right? So the dimension of M3 of R is 9. And if I give you only 8 vectors, or if I give you 10 vectors, well, then you won't have a basis, right? It's too many or it's too few. So it's very good to know these numbers. Again, I'll put this in a box. These dimensions that we're writing down, super important to learn these. And then one more thing, and then I promise I'm coming back to this. One more thing is the matrices don't have to be square size. Does somebody want to propose to me what would be the dimension of the M by N matrices? So these could be any size potentially. Do we have a guess for what the formula is for that? Yordi?
M times N.
M times N. That is exactly right. And again, the standard basis for that would be with these EIJs again. So all of these numbers, guys, we need to know them. We need to memorize them. We need to learn them. It's really, really helpful. Okay, so I did a little bit of a side there. Sorry if I'm making a mess of your notes right now, but I just got so many things I'm excited to share with you that I get a little bit sometimes ahead of myself. But it's just nice to know these numbers, because then when somebody comes along with a problem like this and says, is it a spanning set, Li, both, or neither? I can start. The first thing I would do on a problem like this, if it's on the test, which I'm promising you now, there will be some of these on the test. The first thing I would do is count. How many vectors are there? 1, 2, 3, 4. Just count them. And then what you do is you just compare that with the dimension of V, whatever the universe is that is given to you. And in this case, we know that it's a 4-dimensional vector space, and we were given 4 vectors. And so the people who are maybe suggesting that this could be both linearly independent and a spanning set, which would be a basis, certainly have a good point that these vectors have a good chance of being a basis. But do they have to be? They don't actually have to be a basis. I could give you an even easier example. If I just took, let's just scribble over here for a second. If I just took these vectors in R3, here's 3 vectors in R3. It's the right number of vectors to be a basis, but I promise you, if you put these in the columns of the matrix and you do your EROs, it's not going to go well. You're going to get a bunch of zeros, rows of zeros. The pivots are going to go into the far right column. It's going to be bad news. Right. So we have to be a little careful that we can't just jump to the conclusion that since there's the right number of vectors here, that they have to be a basis. That is unfortunately not true. Let's work it out. Let's actually start solving this one now. I'm going to go ahead. These are my 4 vectors, by the way, V1, V2, V3, and V4. I'm going to lay them out in the columns of a matrix. Now, just so everybody's clear, and I did this in my video over the weekend that I hope you watched, these 4 numbers get smeared into a single column. 1, 2, 3, 4, just like so. And then the second By the way, I started, notice here, I did upper left, upper right, lower left, lower right. I didn't have to do that. I could have started, I could have put, 3, 2, 1, 4 here. The only thing is that however I choose to arrange the ordering of the 4 slots of the first vector, I have to be consistent with that on all of the vectors. So for the second one, I'll do 0, 1, 1, 1. The third one, I'll do 0, 1, 3, 2. And the fourth one, I'm going to do -1, -4, -7, -7. And I'm going to augment that with zeros and number symbols, 0 number symbol, 0 number symbol, and 0 number symbol. Like so. Okay, so I've already got the pivot in the first row in good shape. I'm going to fairly quickly do these EROs, guys. So if you don't want to take all of the notes on this, you could just wait till I get to the final matrix and then write it down. But I will go ahead and show my work here. So if I take -2 times the first row to create a 0 there, I'll get 0, 1, 1, and -2. And then I'm going to do A13 of -3. So that's going to give me a 0, 1, 3, and -4, I believe, and then 0 and hashtag, right? And then I'm going to do A14 of -4. So again, I'll have 0, 1, 2, and -3, and 0 and hashtag like so, right? We have that. Now let's keep going. Have to do a few steps of EROs here. We'll finish this up, then we'll take a break after I get this example done. So I've got my pivot right here. And now I'm going to leave the first 2 rows the same. I'm just gonna go fast here. So first 2 rows staying the same. Don't worry about that too. All that matters is where are the pivots. And then I'm gonna take the negative of the second row and add it to the third row. That should give me 0, 0, 2, -2, and 0 hashtag. And then I'll take the negative of the second row and add it to the bottom row. And I should get 0, 0, 1, and -1, and 0 and hashtag. And now I can see that if I take half of the third row and add it to the fourth row, you guys can see what's going to happen, right? You're going to get a 1 there. That's great. Then you're going to get a 1 there, which is great. Then you're going to get a 2 there, which is great. But look at the bottom row, guys. If you take half of the third negative half of the third row and add it to the bottom row, you're going to get 0, 0, 0, 0. And then I have my 0 hashtag thing here, but see, that hashtag is a pivot in the far right column. And that's bad. That means that it is, actually, we are double bad here, aren't we? So it was the right number of vectors, but it's going to turn out to be a really bad deal because this pivot is in the far right column. That means it's not a spanning set. And this fourth column here does not have a pivot in it, which means the vectors are LD. We spent too much money and we didn't even manage to span the vector space. This one is actually neither. It's actually neither, which I think, David, you have good intuition about that. It's exactly right. These vectors are LD. These vectors are LD. So I can give you the right number of vectors and they could still fail to be a basis. What you'd have to do here, you could remove the fourth vector. That would make the remaining 3 vectors Li, but now you'd have to go back and put in a new vector that would beef it back up to being a spanning set. So you just basically the first 3 vectors that you have here are wonderful. It's just the fourth one was a waste and created a dependency and didn't span the full M2 of R. That's what went wrong. Clear enough? Okay, questions at all? Covered most of the good stuff. After we take a break, I'm going to take some homework questions and also I'm going to try to formally write down for you some of these observations. If I give you too many vectors, then obviously it's not a basis. Can we say anything? If I don't give you enough vectors, that's not gonna be a basis. Can I say anything? And then what if I do give you the right number of vectors? We've now seen that that's not necessarily a guarantee. Is there something we could say there? So I'll try to put that all together for you as we kind of wrap up the class today. But let's take 10 minutes, guys, till about 3:25. Go ahead if you want to get some water, get some fresh air, run around the building a little bit. That would be great. And we'll come back and do some homework problems in just a few minutes. Yeah. Yeah, I think I'll go ahead and get started again. I put a couple of hints on the board over there next to some of the problems that people have put up. Those additional problems on page 335, I'm going to tell you right now, both of them are pretty much a one-line answer. You do not have to actually try to solve those systems. You can just look at them and tell me yes or no if it's a subspace. And I've given you a couple of hints if you're not quite sure what I mean, that will make those page 335 problems. They should take you less than 2 minutes, literally. Very, very, very fast if you look at the right thing. And then on problem number 9 on section 4.4, there's an example in the book that the basic thing on problem number 9 is that they ask you whether a set of vectors spans R3. And of course, normally for that, we put hashtags here. But then there's a second part to the question that asks you to show that those vectors they gave you do span a plane within R3, and they even give you the equation. To do problem number 9, what you need to do is actually not use the hashtags. You actually need to, for once, just keep the XYZ and do the EROs and keep careful track of what happens to those variables as you do those EROs. That's my hint on that particular problem. Otherwise, it works the same as all of the other questions, really. So those are three of the problems over there that I probably won't go in full details with right now. Remember, I do have office hours later, so if this isn't enough help right now, of course, we can talk more in my office. But in the meantime, I did promise, and I do want to do problems 48 and 49 from the last section from the homework. The reason I really want to do these problems is because these are more theoretical. And the reason that I think it's important to look at them is that these definitions over here, right? It's easy to lose these in the background. Like, because every problem you do nowadays, all you're doing is, oh, I'm going to throw the vectors in the columns of a matrix. I'm going to augment it with zeros and hashtags and just turn off my brain and do EROs. This is one of the dangers with Math 250B. We just throw everything in a matrix, we do EROs, and we forget what in the world we're doing, right? It's just like, this is just becoming some mechanical process. And the concept gets lost. So when I ask you these theoretical problems, it brings the concept back to the surface again. And so the definition, for example, of LD and LI is a worthwhile definition to sort of try to understand. This LI definition here, it's a slippery one. I struggled with it when I first learned linear algebra. I was like, I don't quite get it. It's because the definition is kind of in this if-then format. It's like a conditional definition. It's not saying that your linear combination cancels out, and it's not saying that the constants are all zero. What it's saying is if you happen to come across a linear combination of your vectors that cancels out, then you will be able to say that all of the constants are zero. Okay, so it's a little bit of a slippery definition, like I said. So let's try to use that definition to do these problems from the end of the homework for tonight. Number 49, I'm going to start with this one. If we start with two, so this is a kind of a nice conceptual problem. If I start with two vectors that are already Li, and I want to add another vector into that set, the minute I do that, I run the risk of introducing a linear dependency. That could happen, right? I could start with vectors that are Li, the more vectors you throw into a set, right? the better the chances that those vectors will be LD. After all, you're spending another $1,000. Every time you put another vector into a set, a V3 into the set, you're making a more expensive set of vectors. It's a risk that you run. What this problem says, though, is that as long as you add a new vector that is not already in the span, right, the linear combinations of the first two vectors, then that's a safe thing to do. That will be safe. So starting with an Li set, if you throw in another vector, as long as what you throw in is outside of the span of what you already have so far, then that's not going to cost you. I mean, it will cost you another $1,000, but it won't create a linear dependency. So let's try to prove this. And this is for the solution here, this is really what I want you guys to pay attention to, is how am I going to write this up? My job, the job before me is to prove that these three, I'm not even going to worry about the first line yet. I'm just going to look at what is it they're asking me to show. They're asking me to show that V1, V2, and V3 is Li. Here's Li. The only way that those vectors could cancel out in a linear combination is if the constants are 0. Let's grab the bull by the horns and just write down that linear combination. I'm going to assume that the worst has happened. Namely, I'm going to assume that after all, C1 times V1 plus C2 times V2 plus C3 times V3, I'm going to assume that that is 0. This is actually what we are hoping is not true, but let's assume that it is and see what we can say based on that. Okay, what we are going to do is we will show. Does anybody know what I'm going to show? According to the definition, what do I need to show? If I would like to convince you that my vectors are still Li, they have canceled out in a linear combination, what would have to be true in order for this to still be an Li set of vectors? Liam?
The C1, C2, and C3 are all zero.
Exactly. Thank you. C1, C2, and C3, all of the constants are still 0. We're going to show that. I'm going to show that if your vectors have canceled out in a linear combination, then the only way that could have happened was if the constants were 0 to begin with. So to do that, I'm going to play devil's advocate for a minute, and I'm going to, again, imagine the worst. I'm going to imagine for a minute that somehow C3 is not 0. We would like to show that it is 0. So I'm going to convince you that it is 0 by showing you that if C3 somehow was not 0, all hell would break loose, basically, that there would be a contradiction. So here's my question for you guys. So this is what we're assuming right here. This is where I'm starting from. Would you guys agree with me that if C3 is not 0, that I could take that boxed equation and solve it for V3? I think so. Nothing too hard about it. Just move everything to the other side of the equation, isolate the V3 by dividing by C3. So we can do that. So we can actually solve for V3. V3, and it would be, I'll just go ahead and simplify it right away. It would be negative C1 over C3 times V1 minus C2 over C3 times V2. Well, what you're looking at right here, my friends, is something that looks like a linear combination of V1 and V2. In other words, V3, if we can write V3 like this, right, then we're actually expressing it as belonging in the span of V1 and V2. Anything that looks like a linear combination of a set of vectors is in their span. So this thing lives in the span of V1 and V2. Oh, except that we said originally up here that V3 is not supposed to be in the span of V1 and V2. So let me repeat this again. If C3 was not 0, we would be led down a path that would take us to the conclusion that is in direct contradiction to the stated assumption Namely, if C3 was not 0, we would prove that V3 actually is in the span of V1 and V2. So this is a all hell breaks loose conclusion, right? So I'll just say contrary to our assumption. So that is contrary to our assumption. Thus, we must have been wrong. We must have been wrong. It must be true that C3 is 0. Because if C3 is not 0, we get led into this whole problem. And see, if C3 is 0, we couldn't have done that. You can't divide by 0 here, right? You would not be able to solve for V3 if we had C3 being 0, and turns out that's what we have to conclude right here. Okay, well, guys, once C3 is 0, my boxed equation gets a little bit shorter. It gets a little bit smaller, right? So thus, now what I can say is C1 V1 plus C2 V2, that is actually just 0. Just like so. So C1 V1 plus C2 V2 is 0. Basically, I'm just dropping the third term now. This term is 0. And so now what do I have? I have a linear combination of only the first two vectors. What do we know about just the first two vectors by themselves? What's it say up in the question? I know this is an abstract problem. It says that the first two vectors are Li, right? What does Li mean? It means if we ever happen to run across a linear combination of those two vectors that cancels out to 0, and by the way, we've just run across it right here, then we can conclude that the constants must have been 0 for those two vectors, right? For those two vectors. So let's just add that, guys. We're basically done, right? Since V1, the set V1 and V2 is Li, then those constants are 0. So C1 and C2, those are also 0. And now, putting it all together, all three of the constants are 0. So we have C1 and C2 and C3 all equal to 0 here. And that means that my vectors are Li. So hence, we conclude here that V1 and V2 and V3, all three of those vectors are Li. And that's the end of problem 49. Yeah.
Also, so V3 equals C1 over C3 V1. This equation spans V1 and V2, and it's
Right, we have a contradiction here because we've expressed V3 in terms of V1 and V2. This assumption basically says you're not supposed to be able to do that.
Yeah.
V3 is not in the span of
Yeah,
V1 and V2.
So yes, contrary, because the V3 is in terms of V1 and V2,
Exactly.
and V3 is not part of the part of the as
The span of V1 and V2.
the span.
That's right.
Span. It's called spanning set or vector
Just
space?
span, the span
Span.
of V1 and V2.
The span set of V1 V2, and thus therefore C3 is a 0.
Right, right, because we have a contradiction to this assumption here, therefore we make this one.
Got it.
Exactly, exactly, good point. Okay, let's try one more of these. Yeah, Marcus?
Assume V1, V1, C2, V2. equals 0, instead of like it being just say freely.
Right, that's the whole slippery part of this definition that I keep talking about, which is that the way Li is defined is that you have, if you want to convince me that a set of vectors is Li, you have to sort of take the bull by the horns, assume the worst has happened. Namely, that your vectors have canceled out in a linear combination. And then from there, you have to show that, well, it isn't so bad after all, because the only way that they canceled out was that you had to have had all the constants be 0. But you have to prove this part based on assuming this part.
Okay.
Anytime you see a theoretical problem about linear independence, that's how you do it, including this one as well. I want to prove that these vectors are Li. So I'm going to assume the worst. Let's do number 48. I'm going to assume that C1 times the first vector, which is AV1, plus C2 times the second vector, which is AV2, and so on up to Cn times the nth vector, which is AVn. I'm going to assume that that is 0. And we will show, what will we show? How did we do it over here? What were we showing after we made the assumption we have a linear combination of our vectors canceling out? What was it that we were trying to show eventually?
Constants are 0.
That all of the constants are 0. Exactly. So we will show here, in this case, we have n constants, but we are going to show that all of those n constants are 0. Okay. So because I'm a little short on time, I'm going to do sort of the basic algebra part of this quickly. The thing you need to do here is factor the capital A out in front of the matrix. So you pull the A out of everything. So you create A times the quantity C1 V1 plus C2 V2 all the way up to Cn Vn. This is still equal to 0. But one of the assumptions here in this problem, they told us this, that A is invertible. That means that there is an A inverse that we can use, you see. We can actually bring this A inverse into the solution. There is an A inverse, and I'm actually going to do that. I'm going to put an A inverse here and here. On the left of both sides of the equal sign, I'm just going to hit the equation with A inverse. The reason I'm doing that is because what's A inverse times A? Liam? The identity matrix, and the identity matrix is like multiplying by 1. So I can basically drop it, right? I can cancel that. And on the other side of the equal sign, I still just have 0. Because you take a matrix times 0, you just get 0. So what do I have now? The A is gone. The A is gone. All I have left is, oh, this is a linear combination of the original vectors, the V1 through Vn, and that is what's canceling out right here. And what do we know about the original vectors? They're already Li. They're already Li. If those vectors are already Li, that means that, well, if we see a linear combination of those guys canceling out, we can say that the constants are 0. And that's what exactly what we have. We have a linear combination of those guys canceling out to 0. And so since, one more sentence and we're done, V1, V2, and dot, 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 up to Vn, since that is Li, by assumption, we know that, we conclude that all of these constants are 0. That's what Li actually means. That's what Li means. So we're done. That proves it. Okay, so again, we could say thus or hence the new vectors AV1, AV2, and dot 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 up to AVN. That set is Li. That set is Li. I'm overdue for putting one of these on a test. For a couple semesters, I've stayed away from it, but I do like people to know these definitions of linear independence. We won't dwell on this too much, but at least a couple examples to have you practice here. Okay. Get myself a little room here. Let's go back. I'm gonna punt on the rest of those homework questions for now, because I want to take 5 minutes to give you a quick little scenario. Go back to just a couple more minutes to go, but I just want to set this up and make sure that we can kind of appreciate some nice conclusions of what we've said so far today. So let's do this, guys. Let's assume, let's take a vector space V. And I'm gonna take a set of vectors, I'm gonna say, I'm gonna consider the set V1, V2, and dot, 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 up to VK in V. So I'm gonna grab some vectors from this universe. And we're interested in the same question we've been answering or asking all day today, which is, are those vectors a spanning set? Are they Li? Are they both? Or are they neither? I'm gonna write down something here that is gonna be super helpful. I'm gonna ask you, if you are taking notes here, to split your paper into 3 parts. And we're gonna look at 3, basically it's 3 scenarios. I only need 1 minute per scenario to explain this. The first case is gonna be, what if K is bigger than the dimension of V? What if I give you too many vectors compared to the dimension of V? And the second case is going to be, what if I give you not enough vectors? What if K is less than the dimension of V? And finally, what if K is equal to the dimension of V? I would like to briefly just discuss what happens in all 3 cases. And we've seen examples of all of these today already, actually. If K is bigger than the dimension of V, that means I gave you a lot of vectors. If I imagine putting them into this augmented matrix, I want you to draw your matrix to look really, really wide and fat. It has a lot of columns before you get over to this 0 and hashtag. It's a very, very, very wide matrix. It has more columns than rows, right? It has more columns than rows. I mean, we did an example already today. We did the example where we took the polynomial 1 and 1 plus x, 1 plus x plus x squared, 1 plus x squared plus x cubed, and then x plus x cubed, right? We did this example already, this kind of example. We've seen this already today. A wide, fat matrix. What is absolutely invariably going to happen if you have a matrix where there's more columns than rows? You see what's going wrong here? If you have a lot of columns compared to how many rows you have, you're going to have unpivoted columns, which means that you're going to have free variables. Free variables means automatically LD, right? This scenario, these vectors are definitely LD for sure. You guys all see this? LD for sure. If I give you too many vectors, if I give you 5 vectors in R4, we know they're not a basis, but even better than that, we know why they're not a basis. They're LD for sure, right? And they might, I'll add this as an afterthought, they might span V. That is still possible. They could be sort of, in fact, in this case, they did span. In the case of those polynomials, they did span V. But it's LD for sure, and it might span V. So it's definitely not a basis. It's too many vectors. See the situation? Guys, for Friday's homework, half the problems you're just going to count. What's K? What's the dimension of V? And just compare them. If they give you too many vectors, it's game over. They're definitely LD. They're not going to be a basis. What about the other scenario? So let's just wrap this up. The second scenario would be a tall, skinny matrix where I actually don't have enough vectors. So this is the second scenario. Imagine this is a tall matrix that has a lot more. We can kind of make an example here. Suppose that we have a pivot there and there's a bunch of, there's a lot of stuff here. Maybe here's another pivot, but I only have, let's say, that many columns. I don't have very many columns, and now I'm augmenting this thing again like usual, etc. You see what's gonna go wrong here for sure? You're running out of columns, guys. You're going to eventually get to a row that goes zeros all the way across, and that means you are forced to circle that number symbol as a pivot in the far right column. In this case, you cannot span. I'm just going to say cannot span because it's not enough vectors. If I only give you 8 3x3 matrices. Remember the 3x3 matrices, the dimension was 9. If I only give you 8, then that's not enough. That's K less than the dimension, cannot span. And I'll say in this case, they might manage to be Li. They might be Li, but for sure they're not going to span. So if I give you too many vectors or not enough vectors, something is guaranteed to go wrong. You're either going to be LD for sure, or you're going to not span for sure. The only good scenario is this one. But even this one, we saw earlier, this one isn't even a guarantee. In this case, this is the last one, guys, and then we'll call it a day. On Thursday, we'll practice this a bit more. But in this case, this coefficient matrix is exactly a square size. So here you would actually have a square. It's not too tall and skinny. It's not too wide and fat. It's actually a perfectly square size. In this case, it's both or neither. It's both or neither. And I can actually tell you exactly when it's both and exactly when it's neither. So I'm going to have you write this down, and then we'll come back to it next time. What's a trick that we can always use with a square matrix that we don't normally get to do with regular matrices? Taking the determinant, right? And we remember that having a basis would be what I would call a good thing. So that would probably go with the determinant of this matrix being not 0, right? Isn't that consistent with what we would expect? And the neither case would be if the determinant of the matrix was 0. So a few minutes ago, I gave you 4 2x2 matrices that were neither. If you had just taken the determinant of that 4x4 matrix that we set up earlier, you would have gotten 0 and said, yep, it's neither. So in this case, it can't be one without the other. All right, we'll write this down again on Thursday and do some practice with that. And we're going to finish chapter 4 on Thursday. So I will look forward to seeing you guys Thursday. Thank you.
I know you mentioned.
I'm struggling. I should finish it, but there's a lot of here. So are you gonna skip? I'll make them watch a video. So at some point I'll have them watch the video. So Thursday, I should be able to finish chapter 4 on Thursday. I expect that I will. I mean, I also have some group work that I want to do. The group work always takes some of my time away. I have to figure that out. It's so hard to cover everything in this class. I struggle with it all the time. So I'm trying my best, but I really need to finish chapter 4 this week. I'm trying because we have an exam in 2 weeks, so I have to, I don't want to, the thing I really hate is if I have to change what the exam is, because then I have to change all my resources, and that takes me a massive workload. So I don't want to change that. So I will make them watch a video or whatever I have to do to make sure we. Okay. So I just feel like I've been making them do a lot of videos, but it's the only way I can cover everything.
I'll probably make Thursday like a review for chapter 4.
That would be great. That would be perfect for Thursday. Okay,
Sounds good.
yeah, thank you. Yeah, great job. How is it working with the other students that aren't from my class? Are they still coming?
Yeah, they're still coming, but